concavity, and inflection points. Our objective is to use derivatives to determine the concavity of a function. Let's first talk about what concave up and concave down look like. Notice in both graphs there's a section that is decreasing and increasing. Increasing, decreasing. What concave up and down means is where the curve lies in relation to its tangents. For example, if I draw some tangent lines in this graph, notice that the curve always lies above those tangent lines, versus in a concave down graph, anywhere I draw a tangent line, the curve lies below its tangents. In concave up, the curve of the function, we'll call it f, lies above its tangents. In concave down, the curve of the function lies below its tangents. Notice specifically the slopes of those tangent lines. At first, negative slope, then we move to the right, positive slope, and then a greater positive slope. These slopes of the function are increasing. Remember that slope of f can also be described as f prime, so I'll conclude that therefore f prime is increasing. And remember, when something is increasing, that something's derivative is positive. So I'll say therefore the derivative of f prime is positive. Well, the derivative of f prime means f double prime, the second derivative of f. So the second derivative of f is positive. So notice all of these things that relate to being concave up. The curve lies above the tangent lines. The slopes of the function are increasing. The derivative of the function is increasing, so its second derivative is positive. In the concave down graph, where the curve of f lies below the tangents, first we have a positive slope, and then a less positive slope, and moving to the right, now a negative slope. So these slopes are decreasing. Therefore, the derivative of f, which means the slope of the tangent line of f, is decreasing. Therefore, the derivative of f prime is negative, since when a function is decreasing, its derivative is negative. And since the derivative of the first derivative means the second derivative, then the second derivative is negative in a concave down graph. Concavity. Let f be a function that is continuous on the closed interval a to b and differentiable on the open interval a to b. F is concave up on a to b if the graph of f lies above each of its tangent lines throughout the interval, and therefore if f prime is increasing, and therefore if f double prime is positive. These are all important things we need to remember about a graph that is concave up. For a function that is concave down on the interval a to b, then the graph of f lies below each of its tangent lines. Therefore, f prime is decreasing, and therefore f double prime is negative. Let's take a look at this and identify the sections of the graph where it is concave up and concave down, and look at some relationships. So where's the function concave up? Where would it lie above its tangents? Well, at first, it's bending downwards. So any tangent line that I would draw here will be above the curve. The curve is below those tangents. So at first, the curve is concave down until about right there. Well, we can list that as a place where our function is concave down. That's going to be from 1 to about 6. So on the interval from 1 to 6. Then the curve is bending up, such that if I were to draw a tangent line, that curve would lie above the tangent line. So the function's concave up from 6 to 8. Then it switches back to concave down, bending downwards. That's from 8 to 10. The next section of the graph is bending upward. That is going to be from 10 to that sharp point where there is no concavity because there is no bending at that sharp point. So that's at 12. So 6 to 8, union, 13, 10 to 13. And then there will be one more place right after that sharp point where the graph is bending upwards once again. So again from 13 to 14. And then finally, the graph is concave down from about 14 to 16. Now remember, at the sharp point, the curve is not bending, so we can't say concave up or concave down, which is why even though the graph is concave up from 10 to 13, and then again from 13 to 14, we cannot combine those intervals. Now we have a special name for the places where the concavity of the function changes, such as at 6, at 8, at 10, and at 14. Those are called inflection points. An inflection point is where the concavity changes. Now a point is written with x, y coordinates. So what is the point, the order pair, for that first inflection point? Over 6, up 3, that's going to be at 6, 3. Our next inflection point is at 8, 3. Then we have one at 10, 1, 2, 3, 4, 5, about 5.5. Since these are order pairs and not intervals, I'm not combining them with a union, I'm just listing them. So I'm putting commas between them. Finally, the last inflection point is at 14, 4. So remember that a graph is concave down when its second derivative is negative, and a graph is concave up when its second derivative is positive. So to determine where an inflection point will be without having to look at a graph, think about when we change from a negative to a positive, what has to happen? One of two things could happen. At that point, either the second derivative will equal 0 or will not exist. And that's how we can find inflection points. Let f be a function that is continuous on the closed interval a to b and differentiable on the open interval a to b. An inflection point, we often say IP for short, is the point C, f of C, notice an ordered pair, where f changes concavity. Therefore, it can be found where f prime changes from increasing to decreasing or decreasing to increasing, and therefore where the second derivative, f double prime, changes sign. Now we're going to be able to locate these by looking first for where the second derivative equals 0 or the second derivative doesn't exist. Now just because we find those places does not guarantee we have an inflection point. We have to make sure that f changes concavity. Question, is it possible for the second derivative to equal 0 and for f to not have an inflection point? Well, let's think of a couple different example functions. How about simply y equals x? That's that straight line, looks like that. There are no inflection points on here. But notice, if I take the first derivative, I get 1, and I take the second derivative, and I get 0. The second derivative equals 0, yet there are no inflection points. So keep that in mind. Is it possible for the second derivative to equal 0 and for a function to not have an inflection point? Absolutely yes. So just because you find where the second derivative equals 0 or doesn't exist, we still must prove that either the function changes concavity, or the first derivative changes from increasing to decreasing, or the second derivative changes sign. Here's one more example. Let's take y equals x to the fourth. Do we know what that looks like? Kind of like a flattened out parabola. Again, no inflection points. This graph is entirely concave up. But I take the first derivative, 4x cubed. I take the second derivative, 12x squared, and I can set the second derivative equal to 0 and find an x value where that happens at x equals 0. Yet again, there are no inflection points because concavity of this function never changes. So we'll start by finding where does the second derivative equal 0 or not exist, but that's just a starting point. We must prove one of these three things about the function, its first derivative or its second derivative. Let's take a look at some examples. Determine where the function is concave up or down. Then find any inflection points. Justify your answers. So to find where the function is concave up or concave down, we want to think second derivative. Let's start by taking the first derivative. G prime of x is 3x squared minus 12x plus 9. Second derivative next is 6x minus 12. And in order to figure out the sign of the second derivative, we're going to find where the second derivative equals 0 or doesn't exist. This function equals, the second derivative equals 0 where x equals 2. We're going to make our number line and investigate the intervals. And this time, the sign of the second derivative, g double prime. We only have one spot here, 2, and we're going from negative infinity up to that spot 2, and then from 2 to infinity. Again, we're investigating the sign of the second derivative because it's the second derivative that tells us about concavity. Let's pick a test value between negative infinity and 2. 0 is a good one. Plugging in 0 into our second derivative, I get a negative. And then something large on that second interval, maybe 10 would be good, and 10 plugged in gives us a positive. So now I can make my conclusions about the graph of g. When the second derivative is negative, the original function will be concave down, and when the second derivative is positive, the original function will be concave up. So I will say that our function g is concave up on the interval 2 to infinity, and to justify my answer, I will say because the second derivative, g double prime, is greater than 0. Similarly, g is concave down on the interval negative infinity to 2 because g double prime is less than 0. Now we can find inflection points. There is a place where the concavity changes, and that's at 2. So at 2, we have an inflection point. But remember, the point is the x, y coordinates. So the inflection point is going to be at 2, but we need to find the y value. So I plug 2 into the original function, 2 cubed minus 6 times 2 squared plus 9 times 2 plus 1, and that gives me 3. So I will say that the inflection point is 2, 3, and to justify it, we'll say what we observed from our number line, that g double prime changes sign. We could say changes from negative to positive, but no matter which way it changes, there will be an inflection point because the second derivative is changing sign. Number 2, f of x equals the quantity x minus 2 to the 2/3 power. Again, we're finding where the function is concave up or down, so we need to look at investigating the second derivative, find the inflection points, and of course, justify our answers. So to find the second derivative, we've got to go through our first derivative first. So f prime of x equals power rule 2/3 times x minus 2 to the negative 1/3. Using our chain rule, we multiply by 1. Second derivative, f double prime of x, multiply by negative 1/3, that makes negative 2/9, x minus 2 to the negative 4/3. I'm going to rewrite this so it does not have negative exponents. So I have negative 2 over 9 times x minus 2 to the 4/3. Now I'm going to find where the second derivative equals 0, and that's going to be where the numerator of this rational expression equals 0. Negative 2 does not equal 0, so there is no place where the second derivative equals 0. How about where the second derivative does not exist? That's where the denominator equals 0. So 9 times the quantity x minus 2 to the 4/3 equals 0 when x equals 2. Let's make our number line with that x value. Intervals, and because we're looking for concavity, we're going to write the sign of the second derivative, f double prime. Put 2 there, and our intervals are negative infinity to 2 and 2 to infinity. We are looking for the sign of the second derivative. Picking a test value such as 0, I'm going to the second derivative. The numerator, always negative, because that's a constant negative number. And the denominator, well, because it's raised to an even exponent, is always going to be positive. Also, I'm multiplying by a positive coefficient. So this is always going to be a negative over a positive, which yields a negative, no matter what I plug in here. So I've got a negative on both intervals. That means that the graph of the function is concave down on both intervals. And since there's no change in concavity, there is no inflection point. Now, remember that we can't combine intervals with concavity if that's where the second derivative doesn't exist. So we'll make our conclusion by saying the function is concave down on the two intervals, negative infinity to 2, union 2 to infinity, because f double prime is negative or less than 0. And then we'll write why we know there is no inflection point on the function f, and that's because the second derivative, f double prime, does not change sign.